In session 47, we're going to take a look at inconsistent and equivalent equations. At this point, we've been looking at simultaneous equations that have intersected in one point, that one point representing a common solution to both of those equations. We're going to take a look at some exceptions to that. We're going to take a look at situations in which the graphs never intersect and where they intersect one right on top of the other. In fact, they lie one right on top of the other. Let's take a look first of all here at the two equations that are listed here. We have 2x plus y equals 3. Then we also have y equals minus 2x plus 4. What I like to do is to just start graphing these equations and see what's going on here. See if we can detect anything that's going on visually. Well, let's start with this first one, 2x plus y equals 3. Well, what I'd like to do is to go ahead and rewrite this into slope-intercept form. In order to do that, I've got to have y all by itself on the left-hand side with the x's over on the right-hand side. So in order to do that here in this first equation, I'm just going to draw an arrow down here to indicate that we're going to rewrite this equation. In order to do this, we have to subtract 2x from both sides. Well, if we subtract 2x from both sides, we are left with y on the left, and then on the right, we have minus 2x plus 3. Okay, then, with that in mind, let's go ahead and plot some points here. First of all, in this slope-intercept form, we know that our y-intercept is 3, because when x is 0, minus 2 times 0 is 0, 0 plus 3 is 3, y equals 3. So let's go here and plot that first point. X is 0 and y is 3. Now let's also take a look at our slope and label or plot some of our additional points. Our slope is minus 2. What that means is that we have a rise over a run of negative 2 over 1. Or we could have positive 2 over negative 1. Either way will give you the exact same graph. I like to just go ahead and select minus 2 for my rise and positive 1 for my run. And remember, if it helps you to see it visually as far as slope goes, minus 2 is the same thing as minus 2 over 1. Rise over run. So for our minus 2 is going to be our rise. So we're going to start here at our first point, which is our y-intercept, and go down negative 2. Then what we'll do is we'll go over 1 in the positive direction. There's our next point. Starting at this next point, we're going to go down minus 2, which represents our rise, over plus 1, which represents our run. Starting at this point here, we now go down minus 2 over 1, down minus 2 over 1, and so on. Next, we're going to come here to this second equation. And in the second equation, we're going to use its slope-intercept form as well. First of all, our y-intercept is 4. So we're going to come up here, y-intercept of 4. Our slope is also minus 2. So I'm going to put minus 2 over 1 just to help us visually see it. So starting at this point, down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. And if we were to go ahead and connect these points together in a line, and then we came and connected the other in a line as well, we could see that those two graphs will never intersect. They're parallel lines. So in this situation where you have parallel lines, points or graphs that never intersect one another, you have what are called inconsistent equations. They share no solutions in common. And if you just take a look at the slope-intercept form for both of these equations, you should quickly see why. If I go ahead and just remove the one that we had put underneath there, we haven't changed the value at all. But our first equation here says y equals minus 2x plus 4. Our second one, rewritten in slope-intercept, says y equals minus 2x plus 3. Well, obviously we can see here that there are not going to be any solutions for x that'll give us a solution for y that are the same for both of these equations. Those then are inconsistent equations. Next here, let's take a look at two more equations. We have 2x plus 2y equals 4, and we have 2y equals 4 minus 2x. Well, let's go ahead here and start plotting some points and see what we get. If x is 0, y is going to be 2, because 2 times 0 is 0, 2 times 2 is 4, 0 plus 4 does equal 4. So when x is 0, y is 2. So right there then is our first point. X is 0, y is 2. Well, what happens if y is 0? Well, then x would be 2, because 2 times 2 would be 4. So when x is 2, y is 0. Let's choose one more point. If x is 4, what's y? Well, 2 times x is 4 would be 8. Now, in order to get the 8 onto the other side of the equation, we'll go ahead and rewrite this equation by inserting that value of 4 in for x. So 2 times 4 would be 8. We now have 8 plus 2y equals 4. We now need to solve this for y. This y term is being added with an 8, so we need to subtract an 8 from both sides. This positive 8 and this negative 8 cancel, so we are left with 2y on the left-hand side, and over on the right-hand side, 4 minus 8 is negative 4. Right now our y term is being multiplied by 2, so to undo that we need to divide by 2. That then leaves us on the left-hand side y, and on the right-hand side minus 2. So then, when x is 4, y is minus 2. Now then, we're going to go ahead and connect these points together with a line. And there is the graph of our first line. However, if you remember back, how many points do we have to determine a line? We only have to have 2 points to determine a line. So let's take a look then at what happens here in our second equation. Our first ordered pair for this line was 0, 2. When x is 0, y is 2. Well, let's put in an x down here of 0. Well, 2 times 0 is 0. 4 minus 0 is 4. And then we put a 2 for y over here on the left-hand side. 2 times 2 is 4. 4 equals 4. So we can see here that this point here of 0, 2 also works for this equation. Now, if we can find out if one of these two other points works for this equation as well, we know that every point on this line works. Because remember, all you have to have are 2 unique points to determine a line. And if we can show that at least 2 points on this line of the first equation also work as solutions for a second equation, then in fact all the points on this line also work for the second equation. So our second point here that we want to take a look at is x is 0, y is 2. Let's stick an x in here, or 0 for x. 2 times, or excuse me, x is 2, y is 0. If we stick in an x for a 2 for an x, we have 2 times 2 is 4. 4 minus 4 is 0. So the right-hand side will be 0 when x is 0. The left-hand side, y 0, would have 2 times 0 equaling 0. So once again, 0 equals 0. We can see that the ordered pair for this second point of 2, 0 also works. So here we have a situation where the graph for line number 1 is identical to the graph for line number 2. And the reason for that is these two equations are equivalent to one another. They may look a little bit different, but they are in fact equivalent equations. Equivalent equations have the same graph. And if you want to imagine it this way, you can say this graph is here on this plotted graph. If we were to plot this graph of the second line, it would lie exactly on top of this line and coincide with it exactly. So in this situation where you have the same line graph representing two different equations, that indicates that those two equations are equivalent to one another. So then, as a review, inconsistent equations are equations whose graphs never intersect each other, and therefore they have no solutions in common. The graphs of inconsistent equations will therefore be parallel lines. If you remember from your definition of parallel lines never intersect. Second, equivalent equations are equations whose graphs lie one right on top of the other. That is, they are the same line. Therefore, they have an infinite number of solutions in common. And then lastly, the normal simultaneous equations that we've taken a look at several sessions ago, they will have graphs that intersect in one point, meaning that they have one solution in common. That'll end it for session 47.